In this section, we are going to discuss about substitution and elimination reactions of alkyl halides. In this slide, you are seeing a substitution reaction of OH minus, which is taking the place of Cl in propyl chloride. Now, why OH minus is attracted to that carbon? That carbon has a positive charge because Cl is more electronegative, and that attracts electron away from carbon, and that's why carbon is positive. So OH minus is attracted to that positive center. And as OH minus attaches to C, then Cl gets out, which is a good leaving group, and that's how you get substitution reaction. Now there are two types of substitution reaction. One is called SN2 reaction, or nucleophilic substitution bimolecular. It's a single step reaction in which there is no intermediate formed. In other words, no carbocation is formed. As OH minus approaches carbon, in this particular case, Cl gradually gets out. When OH minus is completely attached to C, Cl would be completely out. So both steps, both of these happen at the same time, for which we call it single step reaction. Now this is another problem from the book. You can see here CH3CO2 minus Na plus. This is sodium acetate, and this minus is attracted to carbon. Now which carbon it will be attracted to? The carbon which is most positive. Now how do I figure out that? Br is delta minus is attached to this carbon, and that carbon is positive. So I'm looking at this particular carbon. Now obviously this whole group would then be attracted because it has a negative sign. So that would be attracted to that carbon. Now, as I mentioned before, because of steric hindrance, sometimes reaction could be slow, and this is going to come from the back of the compound rather than this direction, because if CH3COO approaches, let me use another pen, approaches the direction in which Br would be coming out, then they're going to interfere with each other. So in order to avoid that, CH3COO minus goes to the back or farthest away from the leaving group, in this case Br, and that's how product is formed. And we already know how to predict that product, because the leaving group would completely be gone and CH3COO would be attached to that carbon. In this slide, we're going to discuss about reactivity of two types of alkyl halides, 1 degree and 2 degree alkyl halides in substitution reaction, specifically SN2 type of reaction. Now, why the first one is 1 degree? Just to remind you, when the carbon which holds the Br is attached to one other carbon, like in this case, this is the carbon, other carbon is attached, and that's why it's 1 degree. The second one is 2 degree. If you follow, this carbon is bonded to two other carbons, and let me show you with red. This is one, this is the other carbon, and that's why it's a 2 degree alkyl halide. Now the question is, I have OH minus in both reactions, in which case the reaction would happen faster. So OH minus would have all these electron pairs, and obviously it would be attracted to this atom, and this carbon has positive charge and Br has the negative charge. So obviously it would be attracted to that carbon, and then it would go to the back side of Br, and as it approaches close to that carbon, then Br gradually gets out. And that's how reaction happens. Same would be the case in the second reaction with OH minus This is OH minus, is attracted to the backside, and then Br would get out. But the difference is, in first case, there is one big group, methyl group. This is the one big group. Whereas in case of second case, in 2 degree, there are two such groups, and making it much harder for OH minus to approach to that carbon. So these are the two bulky groups. So it's basically they're covering this central carbon atom, making it a lot harder for OH minus to approach to this carbon, which is bonded to Br. And that is going to slow down the reaction. So between 1 degree and 2 degree, substitution reaction will be faster for 1 degree, and it will be slower for 2 degree. In this slide, we're seeing the quality of leaving group. Some groups are much better leaving groups than others. For example, I minus as a leaving group is 30,000 times better than fluorine or fluoride. If you consider fluoride to be 1, I minus is 30,000 times better. In other words, I minus leaves quite readily when a group is coming. Br is about 10,000 times, and Cl minus is about 200 times. So these are all better leaving groups than fluoride. On the other hand, on the right hand side, all these ions you're seeing, they're not very good leaving groups, and they try not to leave. Now let's compare reactivity involving methyl iodide, methyl bromide, and methyl fluoride. Now, why methyl iodide is so much reactive than methyl bromide or methyl fluoride? How do I get this answer? This part is common in every case. You have methyl group, so a steric hindrance could not be a factor here. What is the factor is quality of leaving group. I minus leaves quite readily. So whenever, say for example, OH minus is approaching, then I minus would leave most readily, making room for OH minus. And that's why CH3I reacts much faster than CH3Br, and CH3F reaction is much slower, as F doesn't want to leave that quickly. So our reason for this reactivity variation is due to the leaving group. In this slide, we're going to discuss SN1 reaction, which is also called nucleophilic substitution unimolecular reaction. It happens in two stages. First, there is a formation of carbocation, then the incoming group gets attached. Now let me give you a simple example to explain this to you. Say, and I need to mention to you that this happens fastest for 3 degree substrate. In this case, 3 degree means the carbon that contains the alkyl halide is bonded to 3 other carbon. So that makes it 3 degree. So the central atom here is 3 degree. And say I have OH here, and I want to react it with HBr. So what's going to happen is H is first going to get bonded to this OH. So that OH, so basically this H goes in there. So let me show you this. I think I have more room in at the bottom. C, 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 OH2 plus. And Br minus. Br is there. Now, OH2 is nothing but H2O. So it grabs electron pair and becomes a neutral H2O, and which is a fairly good leaving group. So it leaves as a neutral H2O. So let me show you with the red. So that would be H2O as a leaving group. As a result of this, you're going to see an intermediate carbocation And this is a 3-degree carbocation, which is very stable because it's bonded to 3 other carbons. And 3-degree carbocation is more stable than 2 degree, 2 degree is more stable than 1 degree. So since nature favors something more stable, so 3-degree carbocation, when it's formed, is going to be stable. That means it's going to exist for a longer time and is going to react with incoming Br minus. So Br minus will be attracted to this, and finally is going to form CCCCBr. This is a typical SN1 reaction. So SN1 reaction will be most favored for 3-degree substrate or 3-degree compound, and it will be least favored for 1 degree, which is quite opposite of SN2 reaction. SN2 reaction will be fastest for 1 degree. Actually, CH3OH, even though I wrote down here 1 degree, but that's not right. It should be 0 degree because carbon here is not bonded to any other carbon. So in a strict sense, I think some books they write down 1 degree, but this should be in a strict sense 0 degree, or just says methyl compound. So methyl compound would be most reactive in SN2 reaction and least reactive for SN1 because methyl group doesn't form a stable carbocation because it's 0 degree, and 1 degree also is not that stable. 2 degrees is more stable than 1 degree, but 3 degrees is most stable, and that's why SN1 reaction goes through a 3-degree carbocation and is most favored that way. Now let me give a simple analogy so that you understand the difference between SN1 and SN2. Remember SN2, I gave you just a few minutes ago an example, but let me write down again so that you know the difference. Say I have an halide here, CCBr, and I have OH minus. As OH minus approaches this carbon, Cl gradually gets out. It happens simultaneously, and that is SN2 reaction, and you will finally end up with this compound, this alcohol. So there is no intermediate carbocation formation, so it happens at the same time. Whereas in case of SN1 reaction that I have shown you on the top, there is a carbocation formation before even incoming group Br minus comes in. So this is comparable to the situation, say you went to a ball game and you found that all those chairs are occupied. But as you are approaching, there's a kind person who leaves the chair and makes room for you. So that's the SN2 type of reaction. You are approaching, the other person is leaving. And the rate or how fast the whole thing is going to happen depends upon both of you, both your approach to the chair and person who is leaving from the chair. So rate of filling in would depend upon both of you. And that's SN2. Nucleophilic substitution bimolecular. Rate depends upon both of these compounds. Whereas in case of SN1, situation is like this. You went to the ball game and already there is an empty chair and you just fill in. So there is no living group because living group has left before you even got there. So in other words, this time it's not dependent upon both. It's just depending upon how many empty chairs are there, or empty chair, and that is nothing but carbocation. So that depends only on the concentration of carbocation, which is comparable to the number of empty chairs. So hopefully you understood both SN1 and SN2 reactions. So here I'm summarizing this. SN1, first living group separates, forming a carbocation. Nucleophile then attaches to it. Nucleophile means the ion that is attracted to positively charged species, like in this case OH minus. Gives racemic mixture. Racemic mixture means, let me give you again this example. Say I have a carbocation formation like this. This is flat carbocation. It's not going to look like this. Remember, it's sp2 hybridization. This is sp2 hybridization with 3 pairs of electrons. It would look like this. Pretty flat. So this carbon, carbon, carbon. So this is flat. If you draw this, you'd see that. So OH minus, if for example OH minus is going to be bonded here, or say some other group is bonded, let's assume that Br minus is getting bonded. So Br minus can approach from both sides, can come from the top because this is a triangular plane, or it can come from the bottom. If it comes from the top, you see one kind of tetrahedral structure. If it comes from the bottom, you get an inverted product. So you get mixture of both. If it is R and S possibility, you're going to get equal number of R and S. And that gives you racemic mixture. SN2 reaction, which is nucleophilic substitution by molecular, nucleophilic attack and leaving group separation takes place at the same time. I mentioned that to you, and it gives inverted product. So if you have R, 100% will be changed into S. Now, quality of leaving group, I mentioned this before, but here now I included more compounds, like I have H2O added. So I minus is much better leaving group than Br minus. Then water, neutral water is a good leaving group. Then Cl minus, and F minus is not a very good leaving group. So reactivity involving fluoride is not that great. Now, elimination reaction, I discussed that before, and so it's pretty much repetition. So what I'm trying to do is just to quickly go over this because we discussed this elimination reaction when we talked about formation of alkene from alkyl halide in chapter 4. So basically there are two types of elimination reaction. E2 is a single step reaction. Elimination of two groups take place at the same time. And that happens in anti-fashion. And your final product is the highly substituted products. And we mentioned that before. Now here you're seeing one such example of E2 reaction. You can see X. X could be ClBrI. And here this is the nucleophile. It could be OH minus. As OH minus is approaching, then this hydrogen would be picked up, and then this electron pair would come from this bond to in between carbon and carbon, and then this carbon would have too many bonds, so leaving group has to leave, and then it leaves. So that's what you're seeing here in transition state. It's about to leave when H is also about to get bonded to B. B is just something symbolic. It's not a true representation of any element in this particular reaction. And X is also symbolic. It could be any good leaving group. And finally, both the leaving groups leave, and you end up with an alkene like this. Keep in mind, the leaving group left at the same time, and that's why it's called E2 reaction. E1 reaction is, on the other hand, elimination reaction unimolecular. So here, leaving group leaves, forming a carbocation intermediate. Then the second group leaves. So in other words, it's a two-step reaction, pretty much like SN1 reaction. Only difference is in SN1, both groups don't leave. One group takes the place of the other. That's why substitution, and this is elimination. So whether both groups would be leaving at the same time or one group would be leaving followed by the next group leaving, that makes the difference between E2 and E1. And product formation is guided by Zaitsev rule. More branching gives you greater stability of that compound. In other words, nature favors uh, more branching of alkene. By more branching, I mean if this is an alkene, you'd be looking at what other group is bonded to the double bond other than hydrogen. In this particular case, you have the methyl group on this side, and also these are also considered to be a substituent group or the carbon of the ring. So on the other side of the double bond, also you have two things. One is hydrogen, the other one is part of the ring here, and that also could be considered to be a substituent group. So basically you have three substituent groups in this case. Now you're seeing the mechanism of E1 reaction. Focus on this. This is cyclohexanol, you can see here. Then protonated, it gets hydrogen plus. So this gets protonated. And then H2O leaves as a neutral molecule, and that would generate a positive charge on that carbon, or it's going to make a carbocation. Then carbocation, once carbocation is formed, this hydrogen leaves from adjacent carbon, which is this hydrogen, and there's a new bond formation here. You can see here there's a double bond formation, and that's E1 reaction. Why it is an E1 reaction? First, one group leaves, forming a carbocation. Then the second group leaves, making a double bond. So both groups didn't leave at the same time. Now this just shows pretty much summary of what we discussed. Now I just want to emphasize here, SN1 reaction is most favored for tertiary group and least favored for methyl halide or 1 degree or even 2 degree. SN2 on the other hand is just the opposite, most favored for methyl halide or 1 degree halide and least favored for tertiary, and doesn't really happen because of tertiary. So go over this carefully and make sure you understand the whole topic.